Hello, ladies and gentlemen. Welcome to a new lecture on Discrete Mathematics. In this lecture, I will be talking about counting. Counting and combinations are very important topics in Discrete Mathematics, in computer science, and also in artificial intelligence. You as IT workers or computer science and engineer students, you need to know about counting and combinations. So in this lecture, we will study counting. So the basic counting principles are product rules, sum rules, subtraction rules, and division rules. So the first rule that we study is product rule. The product rule is simply a procedure that can be broken into a sequence of two tasks. If there are n ways to do one task and n two ways to do another task, then we say n1 multiply n2 ways are there to do the procedure. For example, I want to know how many bit string of length 7 are there. When we say bit, it means two possibilities are there, 0 and 1, right? So two possibilities, 1, 2, we have 2 here, and 7 is the length of 7, so we can say to the 7, 128 bit string of length 7 we can make. Another example is here. May you know about the license plates. Every car needs to have one. I want to see how many different license plates can be made if each plate contains a 3 uppercase English letter, this is 1, and 3 digits. So first we should check the domain. What are the possibilities? We know that English letters are each 26 characters, A, B, C to Z. We know that digits are 10. So when we say 3, 26 in power of 3, 10 in power of 3, which gives you 17,576,000 possibilities. And here you can see here, for example, in New York, cars have BBB333 format. It means this one can be 26 letters, this one can be 26 letters, 26 letters, 10 digits, 10 digits, 10 digits. We also have some counting functions. For example, how many functions are there from a set with m elements to a set with n elements, because a function represents a choice of 1 to 1. So we have a choice of 1 of n elements of the codomain for each m element, right? The product rules tell us that the number of subfunction is n multiply n multiply n multiply n, which is n m times, which is n to the m. This is counting functions. Here is one example. You know that telephone number follows some format. It means in Korea, for example, we have 02, for example, 3408 2971. This 02 means Seoul city. This may be area, and this is phone number, right? Or for mobile phones, we have 010 8999 8586. Maybe this is for mobile, just mobile number. This maybe is for SKT. This is for like area, and this. So here is the format of telephone numbers. Here is an example. The North American numbering plan in ANP specifies that a telephone number consists of 10 digits, and that 10 digits, 3 digits is considered as area code, 3 digits as office code, and 4 digits as station code. So totally 10. If we say that X is a variable and it's a digit 0 to 9, N is also a digit from 2 to 9, and Y is a digit of 0 or 1, in the new format of New York, NXX, NXX, XXXX. It means what? It means this one cannot be 0 or 1. It can be 2 to 9. And this XS can be from 0 to 9. In another format of New York, it was NYX, NNX, XXXX. It means this one can be 2 to 9, this one can be 0 or 1, and the X are the same. So the question here is, how many different telephone numbers are possible under the old, this one, and new telephone number? So in fact, for NYX, there are 8 here, 2 is Y, right, and 10 is for X. So NYX is 8 multiplied 2 multiplied 10, which is 160. For NXX, N is 8 possibilities, X is 10 possibilities, and 10 is for x, then 8 multiplied 10 multiplied 10 is 800 for nxx. Then we have again n and x, so 8, 8, 10 is this one. And for xxx, all x's can have 10 possibilities. So we will have 10,000. Then by multiplication, you will have this one. And you can do the same thing to find a new format, which we can find the number of possibilities. The product rule can be phrased in terms of sets. If we have, for example, A1, A2 up to AN as finite sets, then the number of the elements in Cartesian product of those two sets is the product of the number of elements of each set. So by the product rule, we can say that A1, this is Cartesian product, A2, A2M is A1, A2 up to AM. Right? This is the product in terms of sets. Here we have a task and we can accomplish this task in different ways. So we consider a set of ways as N1 and another set of ways to do this task in N2. And you should know that none of the set of N1 ways is the same of N2. It means they are different. In this case, we can say N1 plus N2 as the ways to do the task. Simply we sum them, and this is called as sum rule. Here is an example to better understand. The mathematics department must choose either a student. See, either means or. A student or a faculty. So we can choose student or faculty, right? Member as a representative for university committee. How many choices are there for this representative if there are 37 members of mathematical faculty and 83 student majors and no one is both faculty? So here the question is very simple. We want to select some people as committee member, and we say that they can be a student or professor, where we have 37 professors and 83 students. So very simple. We can select a faculty in 37 ways. Number 1, number 2, number 3, up to number 37. Also, we have 83 students. So selecting one out of 83 is 1, 2, 3. So how many ways do we have here? 37. How many ways do we have here? 83. And some of them is the possible ways. The sum rule can be phrased in terms of sets. A union B equals to A plus B. Or you can say A1 union A2 up to AM. It can be like this. And in here we say that AI intersection AJ is phi. It means they are disjoint. You remember the example of faculty members and students. They are disjoint because a student cannot be a faculty member and a faculty member cannot be a student. Another example here, suppose statement labels in a programming language can be either a single letter or a letter followed by a digit. A single letter means 26 possibilities we have, English alphabets. And when we say letter followed by a digit, again, 26 is the number of possible letters and 10 is number of possible digits. Simple, 26 multiplied 10 plus this one, which gives you the number of possible ways. Choosing password is a headache for users and also for websites, because websites always try to recommend users to select very strong password to not be hacked by some other people. So we want to do combining the sum and product rule to solve more complex problems like passwords. For example, each user on a computer system has a password composed of minimum 6. This is an example. This is not mandatory. You know, some passwords can be only 1, some passwords can be minimum 8 or minimum. So this is an example. We can say 6, 7, or 8 characters long. It means minimum 6, maximum 8. Where each character is an uppercase letter. How many uppercase letters we have? 26. How many digits we have? 10. Each password must contain at least 1 digit. So then the question is, how many possible passwords are there? So in here, we suppose P is the total number of passwords, right? And we say that P6 for this one, P7 for this one, and P8 for this one. It means the number is 6, 7, or 8. To find each of P6, P7, and P8, we find the number of passwords of the specified length composed of letters and digits and subtract number composed by letter. Very simple. 26 plus 10 in power of 6 minus 26 in power of 6, which gives you this number. For P7, 26 plus 10 in power of 7 minus 26 to the 7, which gives you this one. For 8, the same thing we do. Then, according to the sum rule, P is equal to P6 plus P7 plus P8, which gives you this big number. Very simple. The internet means IP. It means if you connect computers by some valid IP address, it means you are connected to the internet, global internet. We have two types of IP. One is IP version 4, we show IPv4, which uses 32 bits, and also we have IPv6, which uses 128 bits. So in here, in this example, we consider IPv4. So in IPv4, we have 5 classes: class A, class B, class C, class D, and class E. So as you can see here, in each class, we have net ID, this is network ID, and this is host ID. Network ID, it means we can have different networks, one for Sejong University, one for Seoul National University, one for Yonsei University, one for different universities, right? And inside those universities, we can have hosts. Like me, I'm connected to the network of Sejong, right? So this is host means user, network means big network, which works under the big network. So in class A, we use 0, it's fixed, and 0 followed by 7 digits here as net ID, and 24 here as host ID. In B, we have 1 and 0 fixed, followed by 14 bits net ID and 16 bits. So we have 7 here, we have 24 here, we have 14 here, and we have 16 here. Sum should be 32. In class C, we have 110 as fixed, then we have 21 net ID and 8 bits as host ID. Class D and class E, these are reserved. Class D is 1110, and the rest is like 28, that is for multicast address, and E also not used, so this is used for multicast. And multicast means one talking to many, right? Like for example, one big server sending email to many. For example, you can say cell broadcast. Every day you receive some alarm message about corona, weather, or climate from the government. Those are considered as cell broadcast, that one station sends information to many users in one area. So this is multicast, and this class E is reserved for research and experiment, so we cannot use it. Research and experiment. So here we can see the characteristics of internet address. In class A, the leading is 0, total is 8 and 24. The number of networks, 128, 2 in power of 7, right? In here we have 2 in power of 24, which gives you this number of hosts, total addresses, and the same. For class B, we have 10, 16, so you can see the rest, and you can see here are not defined, it means they are not used. So this is different topic about internet addresses. So here is an example about internet addresses. How many different IPv4 addresses are available for computers on the internet? We use both the sum and the product rule. If we consider X as the number of available addresses and XA, XB, XC as the number of addresses for each class, then we can do that. A to the 7 minus 1 is 127. To the 4 minus 2 is this one, and total, you can go for it. B to the 14, to the 16, and this. C to the 21, to the 8 minus 2, and this one. Total, 3,737,091,842. This is the possibility. Then we have subtraction rule. If a task can be done either in one ways or in one of the n2 ways, then the total number of ways to do the task is n1 plus n2 minus the number of ways that they have common. The same we have here. A union B is equal to A plus B minus common of them. This is known as principle of inclusion exclusion. Here is an example. How many bit string of length 8 either start 1 or end with 2 digits 00? So here we use subtraction rule. Number of bit string of length 8 that start with 1 is 2 to the 7. Number of bit string of length 8 that start with 00 is 2 to the 6, which is 6. And number of the bit string of the length 8 that start with 1 and ends with 00, it means 3 of them are fixed, 32. So the number is this one. Here you can see 1. How we can do that. The next one is division rule. There are n divided by d ways to do a task if it can be done using a procedure that can be carried out in n ways. And for every way like w, exactly d of the n ways corresponding to this dw. So we can restate in terms of sets. If the finite set A is the union of n pairwise disjoint subset, each with d elements, then n is the a divided by d. And in terms of functions, if f is a function from a to b, and if these two a and b are finite set, then for every value of y into b, there are exactly d values x in a such that fx is equal to y, then b is, this is cardinality. How many ways are there to seat 4 people around a circular table where 2 seating are considered the same when each person has the same left and right neighbor? If you can rotate one seating to obtain another seating, they are considered the same seating. This is also some resources, or they consider it as dining philosophy. So here we want to see the number of ways, number of the seats around the table from 1 to 4. So this is the desk. We have one chair here, one chair here, one chair here, and one chair here. And this is the rotating. Then possible ways to select a person. We can say 4 ways for seat number 1. We can say 3 ways for seat number 2, 2 ways for seat number 3, and 1 way for seat number 2. And this is very similar to 4 factorial. So we can say that there are 4 factorial, which is equal to 24 ways to order the 4 people. But because 2 seating are the same when each person has the same left and right, we say the same neighboring, for every choice for seat 1, we get the same seating. That's why by dividing rule, there are 24 divided by 4 and 6 different seating arrangements. Trees are a type of graphs, they are undirected, and any 2 vertices in a tree are connected by exactly one path. It means we have cyclic undirected graph. We use trees to solve many counting problems, and the branch represents a possible choice. Each branch here are some choices. And the leaves are the last leaves, sorry, these are short choices. And the leaves are for possible outcome. Let's see one example. Suppose that I love discrete math. This is one sentence written on some t-shirts. And these t-shirts came to 5 different sizes. Size small, medium, large, and X large, and XX large. So these are possible size. 1, 2, 3, 4, 5 possible size. Each size comes with 4 color. Each size 4 color. White, red, green, and black. Then we have some constraints. Constraint says X large comes only in red, green, and black. Red, green, and black. It means no white. XXL comes only in green and black. No red, no white. Then the question is, what is the minimum number of t-shirts that the campus bookstore needs to stock to have one of each size and color available? It means the owner of the bookstore, he wants to bring these t-shirts and sell to students, and question says how many it needs that they have all possibilities. So we start using a tree. This is a tree. So different sizes, small, medium, large, X large, and we said for small we have white, red, green, and black. White, red, green, and black. This means white and small, red and small, green and small, black and small. Then medium white, medium red, medium green, medium blue. Large white, large red, large green, large blue. But we have here XL has only red and green and black. So XL red, XL green, XL black. XXL is only green and black, green and black. So just you count it. How many possibilities? 17 possibilities. Well, the next topic, we are gonna talk about pigeonhole principle. The pigeonhole principle is simple but beautiful and useful idea. Very simple. If a flock of 20 pigeons, dove, roast in a set of 19 pigeonholes, as you can see here, one of the pigeonhole must have more than one. Here, 35 holes we have, but we have 36 pigeons. Based on this principle, one hole must have more than one pigeon. The pigeonhole principle says if we have k as positive integer, then k plus 1 objects are placed into k boxes, then at least one boxes contains 2 or more objects. How you prove this one? We go for contraposition to prove. So prove. But in contraposition, we suppose none of the k boxes has more than one object, because here says at least one. We say none, contraposition. Then the total number of objects will be k. This contradicts to the statement where we say k plus 1. That's why it's correct. So we have a corollary here. What is a corollary? It's a proposition that follows from a theorem. We prove the theorem, then we go for corollary. It says a function f from a set of k plus 1 elements to a set of k elements is not one-to-one. For proof, based on the pigeonhole principle, we create a box for each element y, for example, in the codomain of f. Then we put the box for y, all of the element x from the domain. Then we say that fx is equal to y. Because there are k plus 1 elements and we have only k boxes, so we conclude that at least one box has 2 or more elements, and we conclude that f can't be 1-to-1. Here is an example. Among any group of 367 people, there must be at least 2 guys with the same birthday. Why? Because we have only 366 days in my maximum. Sometimes we have 365 days. So at least 2 of them has the same birthday. Here we can see the generalized pigeonhole principle. We say that we have n objects and k boxes, then there is at least one box containing n ceiling division of n divided by k. So how do you prove this? Again, we go for contraposition. We say none of the boxes contains more than n divided by k. So the total number of object is k ceiling of n divided by k minus 1, which is less than k multiply nk plus 1 minus 1, which equals to n. So this inequality of nk, like what we had already, n divided by k less than n divided by k plus 1, has to be used. So the total number of objects is less than n. This is contradiction because there are total of n objects, not less than n objects. Here is a theorem for pigeonhole principle. If we assign m pigeonholes to n pigeons, then at least one of the pigeonholes holds more than one pigeon. This is the principle of pigeonhole. And another theorem we have, if m is equal to p1 plus p2 plus p3 up to pn minus n plus 1, pigeons are distributed in n pigeonholes, then the first hole hosts p1 pigeon or the second hole hosts p2 pigeons up to same. So this is the generalized form for it. Example, suppose we have 100 people and we want to check how many of them born in the same month. So this is 100 number of people here. 12 is the number of months. So ceiling division of 100 by 12 is 9. How many cards must be selected from standard deck of 52 cards? Our deck has 52 cards. We want to make sure that at least 3 cards of the same suit are chosen. We assume that we have 4 boxes, but for each one, right? So we have 4 boxes. And in here, we go for this, we go for this, we go for diamonds, and we go for this one, suppose, right? Then we use generalized pigeonhole principle, which tell us at least one box contains, so this one, n divided by 4, because we have total n of 52 and which are divided in 4, right? So at least one box contains at least n by 4, at least 3 cards of one suit are selected. It means when we say at least n divided by 4, the smallest integer n such that n divided by 4 than 3 is 2 multiply 4 plus 1, which is equal to 9. Next example, among 6 red pieces, 5 white pieces and 7 blue pieces, how many pieces should be taken minimum to guarantee that at least 3 red pieces or 4 white pieces or 5 pieces are there? So we have some, for example, you can say these balls, we have 6 red balls, 5 white balls and 7 blue, right? Then we say how many balls we should take out to guarantee that at least 3 red, 4 white and 5 are there. So based on the generalized pigeonhole principle, we say m equals to p1 plus p2 plus p3 up to pn plus 1. Then we say n equals to 3, right? P1 is 3. P2 is 4, and P3 is 5. So M is equal to 3 plus 4 plus 5 minus 3 plus 1 will give you 10. So this was a lecture about counting. I hope you understand the topic, and please feel free to ask me if you have any question. Thank you.